One of the most important concepts in thermodynamics is called entropy. There are many ways to understand what this is. So let's start with a scenario that will be familiar and that we could use to make an analogy to entropy. Okay, you have 4 dice, and you throw the dice. And what do you show? First you roll a 4, the next one is a 5, then a 3, and lastly a 2. And then you pick up the dice again, and you throw them once more, and here's what you get. The first is a 4, the next is a 4, the next one is a 4, and you guessed it, the last one's also a 4. So in the top scenario, we rolled a 2, here's a 3, we rolled a 4 and a 5. And in the bottom scenario, we rolled all 4s. Which is more likely, to get these numbers showing up or to get these numbers showing up? Your intuition probably says this is more likely. Why? Well, there's more ways to get a 2, a 3, a 4, and a 5. For example, you could have gotten a 5 first, and then a 4 second, and then a 2, and then a 3. Or you could have rolled the first dice a 3, then a 5, then a 4, and then a 2. And there are many, many more. In fact, there are 24 ways to get these 4 numbers. And there's only one way to get these 4. So which of these two systems would you say has more order? Which one has more disorder? We typically would say that the top system has more disorder, and this is more orderly because they're all the same. The other thing we can say is there's more ways for this scenario to occur, and there are fewer ways for this outcome to occur. These are related to entropy. We would say, by analogy, that the top system has more entropy. Why? Because it's more disorderly. There are more ways for this to occur. By contrast, something with a lot of order will have fewer ways to occur. Entropy measures these two things. It measures how much disorder is in a system, and it also measures how many ways there are to produce that system. Let's take that analogy and apply it to some actual physics. Here is a piston and an ideal gas contained inside. And then everything is the same about the two. They're at the same temperature. The only difference is that this system now has more volume. In which case is there greater entropy? Pause the video and try to answer. Before we answer that question, let's consider an analogy that's a little bit closer to some actual physics than rolling dice. We have 3 objects in a small area, and if we move them around, there's some number of combinations of positions for the objects. That's when we put them into a small area. Now let's change the situation. Instead of placing them in this small area, let's put them into a much larger area. What we'll find is that there are many more ways to rearrange these objects. So if you were going to count all the different combinations of positions, there are many more possibilities. Increasing the volume, or the area, produces many more ways to create that state. Back to our original question. Which system has more entropy, this ideal gas or this ideal gas? If we imagine them all spaced out equally, we see something like this. But this is not actually what happens in the gas. There are random fluctuations in density. Sometimes the molecules bunch up over here, sometimes over here, and the same thing is true for this system. But which has a higher entropy? The answer is the bigger volume gas, because there are more ways to have those density fluctuations. There are more ways to rearrange those molecules while still producing this state of pressure, volume, number of moles, and temperature. So a good rule of thumb is that if everything else is the same, then having a bigger volume implies greater entropy. But there are other things we can attach to entropy. Let's say we have a box being held above the ground, and then we let it fall, so now it hits the ground and it stops. Which system has more entropy? Think about randomness and disorder. Over here, there is energy stored in the form of potential energy. The box is being lifted from the ground. It is attracted to the Earth because of gravitational attraction, and we've separated it. So this potential energy is stored in the field. Over here, where does that energy go? Well, it's transferred to the box as heat. When this box slams down, the molecules start vibrating, and so they generate random kinetic energy. They have random motion. That's where the potential energy goes. And which system do you think has more disorder? The answer is it's this one, because those particles are now moving in a random direction. That energy, which we had here, is now degraded. We can't use it to do any useful work. This energy, though, we could convert to useful work. Adding heat, as a general rule, increases the entropy. So this system has more entropy than this system. Why? Because that heat that you add oftentimes is degraded energy. It's energy that cannot be used for useful work. It's disorganized and disorderly. There is an equation that allows us to calculate how much the entropy increases or decreases. S is entropy, and delta S represents the change. Delta Q, we could just call it Q. It's the energy that is transferred non-mechanically. In other words, it's the heat energy. And T is the temperature of the system, or the average temperature, if the temperature is changing. Let's look at a simple example of how the equation applies. We've got a bucket of water, a container, and we throw some ice cubes in there. Energy Q, heat, is transferred from the water to the ice cubes. Now, let's say the ice cubes are really, really cold. We can apply the equation both to water and to the ice cubes. So the water's change in entropy is equal to, well, let's say that there's 150 joules transferred out of the water into the ice cubes. So the water is losing 150 joules of internal energy. It's transferred as heat to the ice. And the temperature on average for the water, let's say, is 300. If we calculate this out, we get negative 0.5 joules per Kelvin as the change in entropy. So the water loses entropy. What about the ice, though? Well, the same 150 is transferred to the ice, and now this is positive because the ice is gaining some energy. The ice is at a lower average temperature, and let's say the value is 200. So this is well below freezing. Freezing would be 273 Kelvin. When we divide, what do we get? Positive 0.75. When we add up the total, we get a positive 0.25 joules per Kelvin. And this is actually revealing in every process that occurs in nature, the total entropy of the entire universe, so that whatever your system is, if the ice is our system, then it has to include the ice and the surroundings, the total entropy will increase. This is a statement of the second law of thermodynamics, and it's the third and final way to state this law.